So we're going to continue with integration by parts. But we're going to kind of learn another method. Let's say you wanted to do this guy. Because your math professor is very mean and they just want you to waste a lot of time. Right? So this would mean you'd have to do int by parts. Well, really 5 times here. You'd break it down one time, you'd get to x to the 4th, then x cubed, then an x squared, and then you'll have a bunch of things. You have parentheses inside parentheses, and then there's a minus sign. Remember to distribute. It's kind of, it'll be kind of annoying. So there's actually another method. So that we call tabular integration. So that's what I'm going to teach you now. Doing for you guys what wasn't done for me. Like my professor would actually give us a problem like that, but he never taught us a shortcut. Like he wanted us to suffer through all this. Yeah, it wasn't very nice. Like why? Okay, so there's something called tabular integration. So it's basically a way to streamline integration by parts, and you can literally do this anytime. I think it's kind of, if you have to do integration by parts one time, I think it's kind of overkill. But if you want to do it 2 or more times, I think it streamlines it very nicely. So I'll illustrate the method here with this integral, and then I'll describe how it works. So again, Liotte and all that still applies. You will still have to identify who's your u. Still use Liotte, because you will know who you need to differentiate and who you need to integrate for this method to work. So here, this guy would fall under your A for algebraic, which is polynomial. This guy would fall under your E, which is exponential. And so you know that your u would be the x. Now once you identify that, what you're kind of going to do is you're going to set up a table, and that's why it's called the tabular integration. Right? So what you're thinking about, here's your x to the 5th, here's your e to the x dx. Now if you're writing this on a paper, you can actually scribble it here. I'm making it extra wide for you to be able to see what I'm doing. And you kind of set up a table. Right, so this goes down here. And you know that this guy's your u and that guy's your dv. So you're going to do what you would do with the u's. You differentiate them, and you keep differentiating it. So what we're going to do is in the u column, repeatedly differentiate. And so let's do that. So you're going to differentiate that guy, you're going to get 5x to the 4th. You're going to differentiate that guy, you're going to get 20x cubed. You're going to differentiate that guy, you're going to get 60x squared. You're going to differentiate that guy, you're going to get 120x. You're going to differentiate that guy, you get 120. And then you differentiate that, you get 0. And you stop when you get 0. Right? And there are more cases in which you need to stop, but I'll tell you how you need to know to stop. In this case, if your u eventually gets to 0 when you keep differentiating, you stop. Okay. So here in the left column, so let's actually put what we're doing here in the u column. Keep differentiating. Right? And here's when you stop. Stop when any of these happen. 1, you get 0. 2, you get to a point where the product in that row is easy to integrate. 3. But 0 is always the first one. If you can get a 0, keep differentiating until you get a 0. But there are functions that you keep differentiating and you'll never get 0, right? Think of 1 over x, right? You keep differentiating 1 over x, you're never going to hit a 0. So you might have to do one of these other things. So you keep differentiating until either you get a 0, or you notice that the product in that row will be easy to easy to integrate, or you get to a point where the product in that row looks like the original. So that's kind of that revolving integration by parts scenario. So I keep differentiating that, I eventually get 0. And what I'm going to do is in the dv, I know for dv I have to integrate, I keep integrating. So in the dv, keep integrating. In the dv column, keep integrating until you get to a stopping point as defined above. Okay. So that's what I'm going to do here. So I keep differentiating, I hit 0, I know I need to stop, so now I'm going to keep integrating that. E to the x is easy, its integral is just e to the x, 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 e to the x. Okay. So what I've done here is I sort of formed a table. Now here's how the method finally comes together. We're going to be taking successive products and we're going to take them along a diagonal. And because there's a minus sign in that integration by parts, you know that if you have the minus sign, you open a parentheses, and then there's another integration by parts, the minus sign, those would multiply and give you a positive sign. So the signs are going to alternate. So how we're going to do it is, if this is u and that's dv, this is going to be your v, right? And so that's how the formula starts. You take the u times the v. So you're going to multiply that. And you're actually going to do that right down the line until you get to that last step. In the first case, it's a positive sign, but then the signs alternate from that point on. And you could multiply across here, and the sign would alternate again, but since that's 0, in this case, it's not going to matter. And now you're pretty much going to write down all these products, and that's going to be your answer. So I take the integral of x to the 5th e to the x dx, and it's literally going to be all these products. It's this times that, x to the 5th e to the x, minus 5x to the 4th e to the x, plus 20x cubed e to the x, minus 60x e to the x, 60x squared, plus 120x e to the x, right, plus, this, it was minus 1, minus 120. Right. Now technically, this last guy in this last row, when you multiply back that way, you're actually taking an integral. So technically here we're going to put a plus the integral of 0, but that's kind of just a constant. So that's where our plus c comes in. So ultimately this guy, if you were to do integration by parts 5 times, and it would be a lot more annoying than this, I know it seems like this took a while, but that's because I was explaining what we're doing. But eventually, if you had to just do this, it'll take no time. It'll take very little time. It'll take definitely a lot less time than you going through integration by parts several times in a row, for sure. So that would be the integral of this. It's going to just be x to the fifth minus 5x to the 4 plus 20x cubed minus 60x squared plus 120x minus 120 e to the x plus c. And you say you've done the tabular method. So that would be the third bullet point, is to multiply along the diagonals, alternate signs, starting with plus. So the very first multiplication is a plus sign, but you alternate the signs that you're multiplying by before. In the last row, multiply straight across. And integrate that. If you get 0, this is just plus c. Yeah.
If it's not 0, you just do the integration and then you add c afterward.
Yeah. So I'm going to give you some examples like that. So this is the easiest case. You do tabular method, you keep differentiating until you hit 0, and then that's just going to contribute a plus c, nothing else is going to change. But yeah, it just comes to you just multiplying these products. Because you're really doing the u times the d, u times v over and over again. And then the integral of v du happens in the last row. But by the time you get to the last row with the 0, that term goes away. Yeah.
How come the integral of 0 goes to c?
Because the derivative of any constant is 0. So the integral of 0 is a constant.
Okay.
Right. It could be some constant that you don't. Yeah. So the indefinite integral of 0 is a constant. It's not 0. The definite integral of 0 is 0, but for indefinite, it's plus c.
Okay.
Okay. And that's kind of the method. That's the method. So let's actually try this on a few more examples. So I want to give you some examples probably where you won't hit 0. But I'll do one more example where you'll hit 0, and then I'll give you some examples where you don't hit 0, and I'll give you one of those examples where we got into that situation where there was the same thing on both sides, and then we have to move to the other side. So I want you guys to be able to deal with that scenario in the tabular fashion. Again, like I said, it's really overkill if you have to do integration by parts one time. I would just do integration by parts. But if you ever realize that there are situations where you have to do something several times, 2 times or a bit more, I think this will be a lot easier to deal with. Or if you recognize that you have 2 things that are kind of going to revolve on themselves, like if I have an exponential and a trig function, eventually I get back that exponential and the trig function, then you can do this way to avoid some confusion. So let's show you doing this example. Let's say, not too different, let's say it's something like x cubed sine x. Integrate x cubed sine x. So what you would do here is you draw that table. You're going to get 3x squared, 6x, 6, 0. I know I'm going to stop there. Antiderivative of sine is minus cosine. Antiderivative of minus cosine is minus sine. Antiderivative of minus sine is cosine. Antiderivative of cosine is sine. And so I stop there. And I'm just going to multiply along these diagonals. Plus sign here, but minus sign here, plus sign here, minus sign here. Going across here just gives me the integral of 0. And so now I can just write this answer down, easy peasy. And And so what I did was like 3 integration by parts just now. And so that's going to be x cubed times minus cosine x. So this actually takes a negative sign. Our positive sign will not have any effect. So that x cubed cosine x. Here, it's a negative times a negative, so this just becomes a positive. Plus 3x squared sine x. Here, this is positive 6x cosine x. This is negative 6 sine x. Plus c. And if you're interested, you can do that using integration by parts 3 times in a row, and then compare the work that you've done in answering that, and then you. So if you don't want to take my word for it, you don't have to. You can actually do it the other way, and then you decide what you like more. So let's do one of those examples where I don't get 0, but I end up in a situation where the product is easy to integrate. Such an example, but I'll just do something off the top of my head, something like x cubed ln x. Technically that's a 1 integration by parts thing, but let me just illustrate that. That will eventually go to 0, so I don't want to do that. Let's say I had 1 over x cubed ln x.
Yeah, but wouldn't you have made the u ln x instead of x there anyway?
Come again?
Like if you would have left it x cubed ln x, wouldn't ln x have been u and x to the third be dv?
Yeah, but eventually if you differentiate x to the third, you would get 0. I just want to give you an example where you don't get 0.
Yeah,
This will also actually. Oh, you mean the ln x would be the u?
Yeah.
Yeah. Yeah. I want to do something interesting. Well, both of those are not bad actually. And there was another way that you could have dealt with it. If you had 1 over x cubed ln x. Technically, you don't even need by parts on that. You could have done like a regular substitution and actually do that one. U equals ln x. Oh, you'd still need by parts, but there'll be an exponential. You'd just swap out a log for an exponential. Okay, never mind. Okay, so let's say you had to do that. In this case, your u would be the ln, right? So one thing you could do is, because the way this kind of set up, the u is on the left side, you could just rewrite this. And then you start to differentiate. But the thing is, once you get to that step, you realize that I have to integrate this because this is my dv. You realize that on this level, this product here is easy to integrate because if I just multiply across, I just get a polynomial. Okay? So this is just me doing one iteration of integration by parts. That's going to be a plus sign, that's going to be a minus sign, and so this guy would be x to the 4th over 4 ln x minus, whenever you multiply straight across, you're taking an integral now. And this really falls directly right back into the integration by parts formula though. So that's x to the 4th over 4 ln x minus x cubed over 4. We can integrate pretty easily. That's x to the 4th. 60.
when you multiply across is when you do the actual
Integral.
integration. Okay.
Yeah, so the integral will happen on the last step if necessary. So notice here, if we had continued, if you just kept going with the u, you would never actually hit 0, so you wouldn't really know where to stop. And then this guy, his power would just be increasing. You'd literally be doing that forever. But you can literally stop the process if multiplying straight across gives you something easy to integrate, because that's a part of the thing that you integrate. Let's do kind of the third situation. I believe we did this guy before. E to the x, was it cosine? Did we do cosine x or sine x? It doesn't. Okay. So when you're doing integration by parts, and both your guys eventually will become themselves, whether you differentiate or integrate, actually doesn't really matter too much when whether you choose as your u and your dv. But let's actually just stick to the process. So this is that. So it doesn't matter here, but let's just do it. Let's just follow the rules so that we don't get in trouble. So I want my u here, my dv here. So what we would do is we'd start to differentiate this, get minus sine, differentiate that, get minus cosine. I can integrate this, it's just e to the x, integrate that, e to the x. Notice that at this level here, if I multiply straight across, I get the original. Right? That's the third situation. That's kind of the situation where you end up with the integral on both sides that you want to solve for, and you need to move it to the other side. So at that point, neither of these guys will hit 0 if I keep integrating or differentiating them. But eventually, you notice that they come back on themselves. It gets to a point in this table where I sort of end up with the original guy back. And so there are going to be two levels of multiplication happening here, and then the integral comes back. So this is going to be a plus sign, a minus sign, and a plus sign. And so I'm going to throw those guys in. So that will be an e to the x cosine x. This will be a plus e to the x sine x. And then this will give me minus the integral of e to the x. And so now you see that guy is on both sides. You can just move him over. So you get that. Yeah.
So the last multiplication there, you had minus cosine x times e to the x, but then,
Yeah.
but since it has a negative, it's not like the original, right?
You pull the
Could
minus
this-
out.
Yeah, you pull the minus out. I put it out here.
Okay, okay, so as long as it looks like
Yeah,
the original.
the function part. Constants, if you're off by a constant factor, it's never going to be an
Okay.
issue. You can always just factor that out.
Okay.
So those are sort of the three different scenarios, but that's the tabular method. You can actually use that, and if you have to do repeated integration by parts or an integration by parts that it's in some way kind of annoying, this might help you, not have to deal with all those parentheses and multiplying out and writing all that stuff down and going to the corner writing, oh, u equals this, dv equals that, du equals this. It can be a lot. Okay, so that ends this section, so, yeah.
Sorry, where did the 2 come from in the second part?
Oh, when I move this over. I added this integral to both sides.
Oh, okay, because it's like the original one.
Yeah, it's the original one that I wanted to solve for, so I moved it over, and so I have 2 of them on that side.
Okay,
So, I really want you guys to focus on doing the test, so If I complete any topics between now and the test, just give me the homework after. So homework due. So the test is on Wednesday and we meet on Friday. So homework is due Friday. So you can do it if you have extra time. If you like studied for the test and you feel like you know everything and you want to really go after the bonus problems, then you can do the homework for this. But I won't require you to hand it in to me until May 2nd. March. You should. Okay. So this completes that topic. I don't think this method is in your book, but I think it's a very good, nice method to know. So we'll move on. We're going to talk a little bit about trig integrals today, and this section is going to be kind of long because of something called trig substitution. Well, there are many other situations as well, but it'll take us a couple lectures to get through this. So that was integration by parts. That is how we reverse the product rule. So that is something that's, again, you only would even think of doing this if substitution doesn't work. Substitution is kind of always the first thing you want to do. So if you're faced with a random integral, and eventually we'll get to that point, eventually by the time we get to the end of the semester, how things are going to look is I'm just going to give you a problem where I give you like 5 integrals, do all these integrals. And they'll all require different techniques, and you need to be able to recognize which technique to use. And so the strategy basically is to kind of do whatever's easiest to get away with first. Right? So the first thing you're going to look, if I give you a random integral, the first thing you're going to do is, can I simplify this to use a basic rule like the power rule? If not, can I do a substitution? If not, then can I do integration by parts or something more sophisticated? And you kind of go through this hierarchy of things that are easier versus harder to solve the problems. And that's kind of how you don't get lost about what to do. You can kind of just run through a certain order of operations when it comes to integral. Substitution is the easiest guy besides just knowing a basic rule. And integration by parts happens if you have a product and you want to actually, substitution won't work, you might try integration by parts. Now we're going to move on to 7.2 where we're going to talk about trig integrals and trig substitution. There are times when we can't get away from this guy, but this is one of those guys where avoid if at all possible. There are going to be some cases where we're kind of forced into using it, but I'll show you there are cases that will look like you might need to use this guy, but you don't have to, and I'd recommend if you never have to do that guy, don't do that guy. He's going to be annoying. We won't see him today, but when we get to it, you'll realize why that guy is annoying. But the idea behind this is to use trig identities. Another reason why I went over that trig review with you guys. Trig identities to help us integrate. And with trig substitution, we kind of combine the substitution method with trig identities built into them and kind of did the super substitution kind of method. But we'll first deal with trig integrals in general. Some situation that has just you integrating various trig functions. So a nice example here would probably be something like tangent squared. You want to integrate tangent squared, how would you do it? Ideas? Yeah?
Let u be 10 square x.
Okay, and what would happen? So if we let u be tan squared, what would happen? You'd find du, I'm guessing. So I'd get 2 tangent x times secant squared. Kind of won't work, there's no secant squared. Yeah?
You could use one of the trig identities, I forget which one, but
So substitution would not work there, not, at least not like that. Yeah?
Like, isn't there one variation on the sine squared x plus cosine squared x equals 1?
Mm-hmm.
If you divide by, yeah, tangent squared x equals 1 minus cosecant?
No, secant.
Secant squared?
So what's the, so you want to use an identity? Use it's 1 plus tangent squared, right? Because there's a cosine squared plus sine squared, and you divide both sides by cosine squared, so you get tangent squared. On this side, you have 1 that you divide by cosine squared, so that gives you secant squared.
Yeah.
So you could actually use that identity to help you. This means that your tangent squared, you can actually think of it as secant squared minus 1. And so the integral of this guy would just be the integral of secant squared minus 1. Now at first glance that might look more complicated to you, but is it? What's the integral of secant squared? We actually know that, that's tangent. Right? We know this right away. We know that the derivative of tangent is secant squared, so the integral of secant squared is just tangent. And of course we know the integral of 1, so that's your answer. Right? So that's the idea. There are times when we need to integrate trig functions, and the idea behind it is we're just going to use trig identities to help us figure out how to integrate these. And there are situations in which, with this guy, this is a pretty standard trig example, but there are times when trig functions are being multiplied by each other, or the trig functions are interacting with each other, and we need to sort of get to a situation where we can figure out how to apply an identity to make the situation easier. So there are several forms that we'll have to do. So we'll look at several forms. The first form I want us to look at is if you have a product of sines and cosines. So let's say you have sine to the mx times cosine to the nx. Right, where m and n are just integers. Integers. Right. Now there's a standard approach to integrals like this. There are 3 kind of situations you'll find yourself in. Well, technically there are 4, but 2 of the situations you can use that idea to deal with the third. So there are 4 situations here. So one situation is, for example, if your m is even and your n is odd, you can have your m is odd and your n is even. You can have m is odd and n is odd, and you can have both m and even. Right, now there are going to be different identities that we use for each of these cases, and sort of the third case we can use either method from the first or second case, but there's going to be a way that applies that easier. So that's the first kind of thing. If we have a product of sines and cosines, how do we integrate them? Well, it's based on how the powers relate to each other. An example. So let's do an example where m is even and n is odd. So I'm integrating something like sine squared x times cosine cubed x. I put a similar problem like this on one of the quiz bonuses. I don't remember exactly what powers I used, but there was something similar to this. Okay. So here's how you deal with, this is case 1. So here's how you deal with this case. If power of cosine is odd, here's what you do. Save a factor of cosine. Then what you're going to do is change the remaining cosines to sines. Using perhaps the most famous trig identity, the Pythagorean identity. Then you do a substitution. Substitute u equals sine. Right? So that would be the standard approach for something like this. So you have an integral where you have an even power of sine multiplied by an odd power of cosine. The thing is, you take the odd power and you factor off one of the guys, and then you do this procedure. So here's how it would look. This would be sine squared x times cosine squared x times cosine. So I save a factor of the cosine and put it to the side. Now it turns out that's the guy that's going to end up being my du. Okay? So that would be the first step, save a factor of cosine. The next thing you're going to do is change all the remaining cosines to sines by using this guy, right? You're obviously going to use the fact that cosine squared is just 1 minus sine squared. And so that's what I'm going to do here. This guy I'm going to replace with 1 minus sine squared. So I'll have a sine squared here, and I'll have the cosine hanging out right here. So now everyone is in sines except that last cosine that's hanging out at the back. And now I just do a substitution. Set u equals sine x. My du is going to be that cosine x dx. That's going to be the guy that I have saved right there. Right? So that guy here is my du. And so now the integral just becomes, my sine is u, so that becomes u squared times 1 minus u squared times du. And so now that trig integral just becomes a very nice polynomial integral. It's u squared minus u to the 4th du. U cubed over 3 minus u to the 5th over 5 plus c. So this guy just becomes sine cubed over 3 minus sine to the 5th over 5 plus c. And that's the antiderivative of sine squared times cosine cubed. The other method, because this is such a symmetric identity, the other way is kind of essentially the same, except whatever role the cosine played in this case, the sine is going to play in the other case. So if you do an example where it's like something like sine to the 5th times cosine squared. So this is case 2. So the idea is if the power of sine is odd, you're going to save a factor of sine. Change all other sines into cosines. Using cosine squared plus sine squared equals 1. And then substitute u equals cosine. So that's what I would do here. So here the power of sine is odd. So I'm going to break that up into a sine to the 4th and a sine, which I'm going to put at the end. So that's me saving the factor of sine. I'm going to want to change all these guys to cosines now, because once the power is odd, if I take off a power, the remaining power is going to be even. And so that guy, I can realize that this is just sine squared squared. So So that's gonna be 1 minus cosine squared squared. So now if I set u equals cosine, my du is equal to minus sine. And so I end up with the integral negative 1 minus u squared squared times u squared du. Which will take a little bit of work to expand that, but it's not a big deal in general. So that would be 1 minus u squared. So that would end up being u squared minus 2u to the 4th plus u to the 6th du. So that just ends up being u cubed over 3 minus 2u 5th over 5 plus u to the 7 over 7 plus c. And now I just replace my u with the cosines. It's minus cosine cubed over 3 plus 2 cosine to the 5th over 5 minus cosine to the 7th over 7. So another example, say I had sine cubed cosine to the 5th. So this is case 3. If both sine and cosine have odd powers, either method above works, but you'll have an easier time saving a factor of the lower power, right? Because if I save a factor of the cosine, then I have to deal with a cosine fourth that's going to break into a sum that I'm going to have to expand the fourth degree of that, and that's not going to be fun. It's much easier to save a factor of sine, and then I only have to deal with the sine square. So you kind of save the lower power. So that's what I'm going to do here. So I'm going to break off a sine because it's the lower power. So I only have to convert a sine squared as opposed to having to convert a cosine to the fourth. So I'm going to change that guy to 1 minus cosine squared. That guy's cosine to the 5th. That's my sine. U equals cosine. du equals minus sine. So my integral becomes 1 minus u squared times u to the 5th du. That's minus u to the 5th minus u to the 7th du. And that gives me u to the 6 over 6 minus u to the 8 over 8. This is minus u as cosine, so that's cosine to the 6 over 6 plus cosine to the 8 over 8 plus c. Right. Now I could have saved the factor of the cosine, but that would deal with me, I'd have to now deal with cosine to the 4th, and that would be 1 minus sine squared squared, and then I'd have to expand. It could work, but it would have been more work. So you want to save a factor of the lower power if they happen to both be odd. If they're both even, you'd use the half and the formula on both of them, but we'll deal with that next time. So I'll see you guys on Tuesday. Yeah, we'll spend a while in this section because there are so many variations of trig functions and there's so many trig identities to take advantage of. We're going to be looking through them for a while.